Alright, so this video goes over the other type of probability. We covered relative frequency probabilities, and so now we're going to look at theoretical probability, and we'll actually probably do a lot more with theoretical. So theoretical probability is the bigger of the two types, right? Theoretical probability is the probability when people are talking about something as a probability, the chance of something happening. Most of the time we're talking about this theoretical probability. It's what we would expect, the actual probability, the expectations, right? An example of the difference between the two is flipping a coin. Right? I understand that when I flip a coin, I've got a 1 in 2 shot of getting heads, so I have a probability of 1/2 of getting heads, or 50% chance. That's theoretical probability. Relative frequency probability is if I did an experiment and I flipped a coin 100 times, I tallied the number of heads that came up on that particular coin. Suppose out of 100 tosses, I got heads 57 times. Well, the relative frequency probability of getting heads in that experiment would have been 57 out of 100, or 0.57, or 57% chance. Again, that's the estimated probability based on experimentation. Right? That's the difference between the two. Relative frequency probability and theoretical. Alright, so theoretical is the one, again, that we typically deal with, and we're going to deal with a little more often in this class. It's the analytical probability, right? Using our knowledge of the nature of the experiment. We're not necessarily going to do the experiment, but if we did, this is our expectation. If we actually ran the experiment, this would be the probability of said event occurring. This is going to require you to use your counting techniques. You're going to have to find two things. You're going to have to find the universal set, where the universal set is always equally likely outcomes, and ours always will be. And then find the probability of an event occurring is basically taking the probability, or taking the number of outcomes total. That's our divisor, the big universal set, and finding the number of event outcomes, what we consider favorable outcomes. Again, favorable outcomes means that's what we're counting. We want to know how many times this will happen. Right? If I'm flipping a coin, how many times head will occur? Well, the favorable outcome is 1 out of a possible 2, which would be my universal set. Alright, so the number of ways the event occurs in my universal. And then it's, again, just a simple division. The hard part is, again, using our counting techniques to solve for these two numbers. I have to find the number in my universal set, and I have to find the number of outcomes that I'm interested in, that I want to know the probability of, from my universal set. And then you do a division, and this number should always come out between 0 and 1. Right? Probability is always between 0 and 1. Alright, so the first example is a card example. So again, I'm giving you here the deck of cards, which we practiced in the last. Again, this is where we'll be using Chapter 6. Alright, so all of this will be Chapter 6 information that we'll be utilizing. Alright, so there's our standard deck of cards. Suppose the experiment is, I'm going to randomly draw. So randomly is where we get the equally likely. That's why we use that term. Randomly means every single card in the deck could be picked. Right? Again, every single card in the deck could be chosen. That's where the randomly is. And there's my 52 cards broken down by suit. All right, find the probabilities. All right, so find the probabilities of drawing a diamond. All right, well, probability you get a diamond would be the number of diamonds out of my universal set. Well, out of the 52 cards, there are 13 diamonds, which reduces down to 1/4, or 0.25, right? A quarter of the deck is diamonds. So if you were trying to get a diamond, when you draw a card, you have a 25% chance of getting that diamond. Right, probability of drawing a 5. So probability you get a 5. Well, it's the number of 5s, number in my universal. Alright, so out of 52 cards, how many 5s are there? Well, it didn't say what suit, so I could pick any of the 5s. Well, there are 4 5s. Right, so 4 out of 52, which reduces down to the fraction 1/3. And then the decimal approximation for that, if I type that out in the calculator, is 0.769. So a little bit better than a 7% chance of drawing a 5 from a standard deck of cards. Well, what's the probability I get both of those events, right? So I'm combining them. I want the probability I get a diamond and a 5. So basically, I'm looking for the card that is a diamond and a 5 at the same time. Well, there's only one of those, right? That's it. There's only one possibility out of 52 that I'll get a diamond that's a 5. Alright, so 1 out of 52. Which again, the decimal approximation, 0.192. A very small probability, right, around 2% chance. Alright, those are all, again, fairly straightforward and easy cases. We're going to ease you into this theoretical probability. So again, those were, what do we consider those easy outcomes? Alright. Or is always the one, again, you got to be tricky with. You got to be careful with table examples in the relative frequency cases and in the theoretical case when we're doing the or. Always make sure nobody gets counted twice. Alright, so I want a diamond or a 5, which means they could be diamonds or they could be 5s. There's the case where the diamond is also a 5, and I don't want to count that guy twice. Alright, so number of diamonds or 5s divided by the number in my universal. Well, I know there are 52 cards. Out of 52 cards, well, how many possibilities are there for me to draw a diamond or a 5? Alright, so if you look at my universal set, there are all my diamonds. There are all my 5s. I don't want to count this guy twice. So if I were setting this up with the formula, there would be 13 diamonds, 4 5s, and I counted one of them twice. And so what I want to make sure I do is, well, that would be 17, but minus the one I counted twice, so it's really just 16. Or you could just go ahead and count them, 13, and then add 3 more, comes out to be 16. So there are 16 cards that are either a diamond or a 5, and I only count that 5 that's a diamond one time. Alright, then the decimal approximation to that comes out 0.3077. Alright, about a little over a 30% chance of drawing a card that is either a diamond or a 5, one or the other. Our next example is going to be our dice. Like I said, we're going to do all the same examples in this chapter as we did in chapter 6. So this is a dice example, rolling 2 fair 6-sided dice. Right? They're distinguishable. Ours will always be distinguishable cases. If they're not distinguishable, they're not equally likely, and we can't use theoretical probability to find it. Ours will always be. Alright, so suppose 2 fair-sided dice are rolled. Alright, here's the 36 outcomes I've got listed here for you. The first one, so this is, if you remember, in the last video, we did an experiment case of this, where we did an experiment and out of 200 rolls, we had so many outcomes that were sum of 2, so many outcomes that were sum of 6. Alright, so those were expected probabilities or estimated probabilities based on my experiment. Well, now we're going to look at, well, what's the theoretical probability? What's the actual expected probability? Alright, so we want to know the probability that we get a sum of 2. Well, probability we get a sum of 2 based on what we understand about rolling 2 dice. Well, it's the number of ways to get a sum of 2 over my universal set, all possible outcomes. So out of all 36 possible outcomes, how many ways are there to get a sum of 2? Well, there's just that one way, right? 1 is the only outcome possible that has a sum of 2. So there is a 1 in 36 chance, which if I write that out as the decimal approximation, a 0.02, which was different if you went back and look at the earlier notes. I think that came out at 7% when I did my experiment. And again, that can happen with experimentations. Your numbers can be significantly off. Now, what the rule is there's the law of large numbers. The bigger the set, the closer you'll get to the actual probability. And we'll talk about that a little more in chapter 8. Right, but the probability based on the theory, what I understand about how dice work, is I have a 1 outcome out of 36 that I can get a sum of 2, and so the probability of that happening is almost 3% chance. Alright, what's the probability to get a sum of 6? Or I think in our experiment that was like 14%. Well, let's see what it is in our theoretical probability. So number of ways to get a sum of 6 out of my universal. So out of the 36 possible outcomes, how many have a sum of 6? If I go up here, remember sums go diagonally, there are all the possible outcomes in my experiment where I can get a sum of 6. So 5 out of 36. There are 5 chances out of 36. Which, written as a decimal, that comes out 0.1389, which is a little closer to what my experimental one was, right? My experimental one was 14 and a half, I believe. But this would be our expectation, right? If we did the experiment, this would be our expectation. If we, again, did a very large set, it should be pretty close to that. Alright, again, basically all of the same ones that we did in Chapter 6, we're going to do here in Chapter 7. So this would be the type of problem that we'll ask when we're doing a sequence of letters, alright? So this is, again, that word computers, again, the 9 letters in the word computers are to be used no more than once each, so no repeats. To form a sequence of 4, so I'm going to pick 4, so I'm going to write that down so I remind myself. So pick 4 of the 9 letters. Alright, sequence means we have order and there's no repeats, which means it's a permutation type. Right? Which I'm going to actually not use the permutation formula, but if you want to use the permutation formula, can. I think with these sequences it's actually easier to use the subtraction method. But like I said, if you want to and feel comfortable using the permutations method formula on the calculator, use the formula on the calculator. Alright, so what are we actually looking for? So suppose a sequence, random just means it's randomly done. Alright, every possible sequence could be selected. Right, find the probability the sequence contains the letter R. Alright, so we want to find the probability that we pick R. Alright, so it's the number of ways to get R out of our universal. And so what this is we're going to use the exact same counting techniques we did in Chapter 6, but we have to count 2 things every time. So you have to get a little more efficient at this, and hopefully because we've practiced it, you have gotten more efficient. I have to find the subset, how many ways can I get R, and the universal set. And sometimes it's easier actually to find the universal, so I'll actually start with the universal set because it's the easier one. And I'm going to do my work here, and then once I figure out my outcomes, I'll plug them into the division, the fraction. Alright, so number of ways to get my universal set. So remember, my universal set means I can pick any letter, right? Pick any 4 of my 9 letters. So this would be, I have got 4 spots I'm selecting. My first choice had 9, my second choice had 8, my third had 7 and 6. You could use the permutations formula. It would be permutation for, not 4, 9, choose 4, right? And it would give you the same number either way. So again, you pick which method you're more comfortable. I actually think for these it's simpler to use the subtraction, but if you want to use the permutation formula, again, both of them are correct. If you do multiply those out, it comes out to 3,024. Alright, so that's my total. There are 3,024 different sequences of 4 when I'm choosing from 9 different letters. Now my subsets. How many of the 3,024 contain the letter R? Alright, so always start with what you want. I want to pick R, but there's more than that to just picking R. R could show up in the first spot, second spot, third spot, or fourth spot. So not only do I have to pick R, but how many places can R show up in my sequence? I'm just going to say and place R in the sequence. Right. After I've picked R and placed R in the sequence, figured out how many ways I can do that, right? How many ways can I pick R and place R in a sequence? Then I have to finish off my sequence, right? Which means I still have 3 letters left to pick that can't be R. So I still need 3 letters, 3 others, to fill in the 3 places left. Which this is where you could use your permutation if you want to. Right, I'm just going to use multiplication, so how many ways are there to do that? And how many ways are there to pick the 3 letters that are left over? Alright, so pick R, well there's only one R. Alright, so I've picked R, there's only one of him. Places, well I could have R in 4, right? R could be in the first spot, or the second spot, or the third spot, or the fourth spot, right? All of those are different outcomes. So there are 4 places the R could show up. Alright, then once I've picked R and figured out what place he is in my sequence, I have to finish the sequence with other letters. And they can be any other letters than R, so there are 8 other letters sides are. So in the first pick, there's 8. The second pick, 7, and then 6. You could use permutation 8, choose 3 would work as well. Alright, so again, it's up to you if you want to use the permutation or the multiplication. I prefer the multiplication method, but that's just my personal preference. Alright, so if you multiply that out, that comes out to 1,344 of my sequences contain the letter R, so that goes up into this fraction here. 1,344 out of my 3,024 contain the letter R in my sequence, and then we divide that out on the calculator. So you do the division, and it comes out, it's actually 4/9 if you reduce it, and so it's 4.444 continuous is the probability. So 44% chance of that happening. Alright, next one. Alright, our bag of marbles, bag of candy. We'll be seeing bags of marbles, bag of candy. And so this is how they'll be worded now. They'll be, instead of counting, instead of finding sets, we're going to find probabilities. And so with probabilities, there are two things. You still count, you just have to count 2 things. Alright, so I've got my bag of marbles that has 3 blues, 4 red, 1 green, 2 yellows. I'm going to pick a handful. So again, as soon as you see a handful, combinations, we're going to pick 5. And we have how many? 7, 8, 10. So out of 10. Alright, so that's the counting technique. Now we want a probability that, so what are we looking for? Probability the handful contains at most 1 red. So at most and at least, you're going to see those. You got problems with at most on the quiz, at least on the quiz. Alright, you have to be able to find the probability of at most and at least. Alright, so we're looking for the probability we get at most 1 red. So I need to figure out the number of outcomes that have at most 1 red out of my universal. And again, I'll find that fraction in a second. I'm going to do my work down here. Alright, so the universal set's the easier one, so I'm going to start with my universal set. Number in my universal. Remember, universal means I can pick any. So it's a combination. I can pick 5 of any of my marbles. Well, there are 10 of them, right? So this would be where I kind of figure out my universal set. I'm going to pick a handful out of 5 in this particular bag of marbles. I reach in, I grab 5. There were 10 possible outcomes, 10 possible marbles I could have picked. So combination 10, choose 5. Type that in the calculator. Combination you have, unlike permutation where you could figure that out without the calculator, without the formula. Combinations you can't. Combinations you have to type that into the calculator formula. And so when we do, that comes out to 252. Alright, so that would be the universal set. Alright, so I figured out the universal set. Alright, now the subset. Alright, number of ways to get at most 1 red. So remember what at most means. That's my maximum. 1 red or fewer reds. And so I want 1 red. Leave a blank spot because I still have to pick 5. Right, or no reds. Right, we left a spot here because remember we have the hidden and statement. If I want 1 red, I still need 5 marbles. So I have to complete my handful. Right, 1 red and 4 others. And remember, others mean any of the other colors but red. Or no reds, which means all 5 are the others. Alright, so combination, I'm going to pick 1 of my reds. I have to go figure out how many reds I have. 4. And we multiply, I need 4 of the other colors. Well, if there were 4 reds, that means there should have been 6 of the other colors. But I'm going to double check. So 3 and 6. Yep, 6 of the others. Or, so you add, combination, I'm going to pick 5 of the 6 others. Right, and there's my subset that I'm looking for, the event that I'm trying to count. Alright, so you plug those into the calculator, that comes out 4, 6 choose 4 on the calculator comes out 15, And 6 choose 5. Comes out 6. So we got 4 times 15. Which is 60 plus 6, so we get 66. So 66 handfuls, right? So there's my subset. So 66 of the handfuls, so 66 out of 256, have at most 1 red marble, meaning they have 1 red marble or none. And then you do your division. 66 divided by 252 comes out to be 0.2619. Right? And there's the probability that if I have this particular bag of marbles, I reach in and grab 5 marbles out at a time, I'll get at most 1 red marble about 26% of the time. All right, 26% chance. All right, on your own, all right, try flipping a coin. We did some coin examples in 7.1, so you should be able to do those. So try the coin examples on your own. Like I said, I'll post the answers to this later on in the week. All right, so that's sort of, again, theoretical probability. We're going to do basically spending the next few sections, 7.3 and 7.4, is all on practicing theoretical probability, going over a few more rules, and even touching on relative frequency probabilities. All right, we're not done with 7.2 yet. There is one more part to 7.2 where we're going to talk about probability distributions, all right, how to find those. So that's the last video from the 7.2 notes. All right, we're going to stop that there, and we'll pick up probability distributions in the next set of notes.